So hello friend, I Dr. Mohan Verma from Department of Applied Physics, Sri Sankaracharya Technical Campus Bhilwai. Welcome you all in this lecture number 10.2. This is also the part of CS2 Physics Learn with me, lecture on some special topics, and today's topic is laser and introduction and its mechanism. I will also include in this lecture the Einstein's AB coefficients. So outlines the objectives and prerequisite of lecture, introduction to laser, the characteristics of laser, quantum process, the detailed mechanism of obtaining laser, relation between Einstein's A and B coefficients, requirement of lasing action, and finally the summary of this lecture. So objectives and prerequisite. The objectives of this lectures are to introduce the laser and its comparison with light, to discuss the mechanism of formation of laser by using detailed mechanism, and to explore Einstein's AB coefficients and their mutual relations. The prerequisite for these lectures, I expect from my students to have the knowledge of quantum theory of light and the interference of the light. Introduction to the laser. Laser is an acronym for light amplification by stimulated emission of radiation. This is first time coined in 1957 by laser pioneer Gordon Gould. In 1960, laser was introduced as an applying method for production of high directional, coherent, monochromatic, and the polarized light beam. The principle of laser is based on the phenomenon of stimulated emission of radiation. This is given by Einstein in 1970. The first laser device was a pulsed ruby laser. It was demonstrated by Theodore Maman in 1960. In the same year, the first gas laser, helium neon laser, and the first laser diode were also introduced. The characteristics of laser. So to compare with ordinary light, the laser will have this following four characteristics. These are the coherency, directionality, monochromaticity, and high intensity. So first, the coherency. The light from a laser is said to be coherent, and the meaning of this that is the wavelength of the laser light are in phase in space and time. So if any wave or especially that laser have the constant phase or phase difference with respect to time and space, that's why it is known as a highly coherent beam. It is highly monochromatic. The light from a laser typically comes from one atomic transition with a single precise wavelength. So the laser light has a single spectral color and it is highly monochromatic light available. Maximum deviation in its monochromaticity is about 10 angstrom. High directional and collimated. Laser emits light that is highly directional, narrow beam divergence. The light from laser emerges in an extremely thin beam with very little divergence. Therefore, the beam is also highly collimated. High intensity. The intensity of wave is actually the energy per unit time flowing through a unit normal area. In the ordinary light source, the light is spread out uniformly in all directions. In laser, the light spreads in a small region of space, so its intensity is very high. Now the principle of working of laser. The principle is mainly based on its quantum mechanical theory. So these are classified into three types of transitions. One is the absorption of radiation, second is spontaneous emission, and third is stimulated emission. So this is the first type of transition, which is known as absorption transition. So this is the ground state where these are the discrete energy levels, and this is the ground state, and this is higher energy level, which is also known as the excited state. So in general, at ordinary condition, atoms are at the lower energy level when the energy is given in form of photonic energy, and this energy is equivalent to the difference between these two energy levels. Then after absorbing this photon, this atom excites up to higher energy level, and this is because of absorption. That's why this is known as absorption transition. So now this is at the ground state. After absorption, the atoms excites up to higher energy level. So mathematically, it's the probability rate P12. This is actually proportional to that energy given, that energy density, as well as the total number of atoms present here at a ground state. And we use one Einstein coefficient. This is B12, where this 12 gives the direction of transition. So P12, it is actually equal to B12 N1 U, which is actually the function of frequency. So this B12, this is the constant proportionality, which actually depends on the properties of this energy levels 1 and 2, and this actually gives the total probability of existence of the total probability of absorption transition. At higher energy level, now this is the atom at higher energy level after absorption transition. At higher energy level, its lifetime is very small, and that is only 10 to the minus 8 second. So after 10 to the minus 8 second, these atoms come back to ground state automatically by emitting absorbed photon. And this is the emission of photons, and which is actually being spontaneous. That's why this is known as spontaneous emission. So the probability of this spontaneous emission from state number 2 to 1, it only depends on that total number of atoms available at higher energy level, and also that properties of that energy level 1 and 2 with this Einstein coefficient A21. Again, this 21 gives the direction of transition, and this A21, this Einstein coefficient, and the physical significance of this Einstein coefficient is this actually gives the total probability of transition from higher energy level to lower energy level spontaneously. This is one of the important transition, which is known as stimulated transition. So before 10 to the minus 8 second, when the atoms are at higher energy level, when we give one additional external photon to the atoms of this higher energy level, now the atom stimulates back to ground state by emitting two parallel photons. One, it has already absorbed through absorption transition, and second, we are giving to these atoms at higher energy level. So this gives two parallel photons after stimulated transition. So this third type of transition is known as the stimulated or triggering transition, which actually depends on the properties of these energy levels, as well as total number of atoms at higher energy level and this energy given at higher energy level. So this is the third type of transition, which is known as stimulated transition, and mainly this is coined by Einstein in 1917. So the total rate of that emission transition, which is P21, 21 stands for 21. It is now two parts. One is through spontaneous transition, and second is through absorption transition. Second is through stimulated transition. So after that stimulated transition, one chain reaction is to start. This is that single atoms given to the higher energy level. When this stimulate one atom, then that atom come back to ground state by emitting two parallel photons, and these two parallel photons again stimulate two atoms, and each atom give two photons. Then we have now four photons, and four photons further stimulate four atoms, become 8 and 16 and so on. So we have now 2 raised to the power n photons after stimulating n atoms at higher energy level. So all these photons are parallel and follow the conditions for the stimulated that constructive interference. So after constructive interference of these parallel photons having all those conditions required, and we get a single photons of high amplitude as intense high intensity, which is known as laser. So one can say this stimulated transition is mainly responsible for that emission of laser, although that absorption transition and spontaneous transition is also one of the part of this phenomena. Now the relation between Einstein's A and B coefficients. So at equilibrium, what we are observing here, that P12, that rate of probability of transition from atoms to ground state to higher energy level, is equal to the rate of probability of transition from higher energy level to ground state, either through spontaneous transition or stimulated transition. So one can write this is equal to P12 and this is equivalent to P21, this part is spontaneous transition, and this part is of stimulated transition. So by calculating this for that energy density u nu, this is equivalent to N2A21 by N1B12 minus N2B21, and further when we pick out this B12 common here, then we will have this A21 by B21 multiplied by N2, and this is N1 by N2, and this is the simple redistribution of this formula. And now we will use Boltzmann distribution law. According to this Boltzmann distribution law, this is actually that limiting part of that Fermi-Dirac distribution function we have used in that quantum mechanical phenomena of electron distribution in different discrete energy level in quantum physics or in semiconducting physics. So this N1, this is proportional to exponential of minus E1 by KT, where this K is Boltzmann constant, E1 is that energy, and T is that temperature, which is constant at every energy levels. And N2, this is proportional to exponential of minus E2 by KT. Again, this is E1 and this is E2, the energy values at a different ground state and higher energy level. So after calculating this, we will have this N1 by N2 is equivalent to exponential of minus E1 minus E2 by KT, where this E2 minus E1, that is equivalent to h nu, that photonic energy. So one can write this N1 by N2 is equivalent to exponential of h nu by KT. So by putting this N1 by N2, we will have this energy density u nu, it is equivalent to h1 by b21. So h nu by exponential of h nu by KT multiplied by b1 to this minus 1, and that is h2. So now we will compare this with that standard Planck's hypothesis of quantum theory of light. So according to Planck's theory of quantum theory of light, we have this nu u nu, it is equivalent to students have to remember this particular formula. So because we are not able to derive all this in this stage, so that u nu is equivalent to 8 by h nu cube by c cube multiplied by 1 upon e h nu by kt minus 1. So when we compare this with that previous equation, we will have a21 by b21, that is equivalent to 8 by h nu cube by c cube. And this is one relation between these two coefficients, a21 by b21. This is corresponding to spontaneous emission, and this is corresponding to stimulated transition. So this is equal to 8 by h nu cube by c cube. And here this b12 by b21 can be written as equivalent to 1, because this b12 and b21 we can write equal. These are equivalent, because the probability of spontaneous transition is equal to probability of stimulated transition if all the physical conditions are identical. We have taken identical energy at identical time, so these coefficients will be identical. So these are the relation, mutual relation between Einstein coefficients. Now conditions for light amplification, as I have mentioned in that previous slide, that stimulated transition is so mainly responsible for getting laser. So at the thermal equilibrium, the ratio of stimulated and spontaneous transition are generally very small, and stimulated transition is negligible. Then the ratio is given by this. So the stimulated transition is mainly responsible for releasing laser. If you want to have high intense beam, then anyhow we have to enhance the numbers of stimulated transition. So let's compare this stimulated transition with spontaneous transition. So mathematically this stimulated transition can be written as equivalent to b21 n2 u nu, and this is a21 multiplied by n2. So just by cancelling out this n2, we will have this b21 u nu by a21, and the ratio of stimulated transition with absorption transition, we have this stimulated transition upon absorption transition, that is again the same formula, and b12 n1 u nu, and this b12 and b21 can be cancelled out, because total probability we have taken identical in absorption transition as well as stimulated transition, because all the physical conditions are identical, and that this is equal to n2 by n1. So we have this one equation, this is another equation, and what is our target is, anyhow we have to enhance this stimulated transition. So in order to enhance the numbers of stimulated transition, by following this first equation, we can say these are the coefficients, so that energy, radiation energy density made to be larger. So we want to have this larger value of this energy density to gain that stimulated transition. In second condition, stimulated transition is only possible having higher values when this n2 is greater than n1 by using this relation. So we have these two conditions. U nu must have very larger values. Second, n2 must be greater than n1. This is known as a population inversion condition. We will discuss in next lecture for this. And these two conditions are essential conditions. And if anyone fails, then one cannot get laser. So summary: in this lectures, following points were discussed in detail. So introduction to the laser, characteristics of laser light, and that mechanism of obtaining laser, and the relation between and B coefficient, along with that required condition to release laser. So those two essential conditions. Thank you all.